Welcome everyone to a brand new explainer. Today we're doing a complete bottom-up build of a topic that is literally the invisible backbone of our modern skylines. We're talking about IS 4014-1, Code of Practice for Steel Tubular Scaffolding.
Have you ever looked up at a towering skyscraper under construction and wondered what exactly is keeping those workers safely suspended hundreds of feet in the air? I mean, it's not magic, right? It's meticulous engineering, strict standardization, and an intricate web of heavy-duty steel.
And before we lay down our first baseplate, a quick reminder. If you have liked this video, like, share, and subscribe to the ISO Automation Lab channel. It ensures we can keep delivering these deep technical explainers right to your screen.
Okay, let's dive into this. We are going to follow a logical bottom-up build today. So we'll start with an intro to IS 40141-1. Look at steel grade YST22, examine scaffold support component anatomy, compare independent versus put-log scaffolds, and wrap things up with a maintenance and storage tutorial.
All right, Part 1, Intro to IS 4014-1, the foundation of temporary structures. But to really understand the blueprint of this standard, we need to jump straight to the source material in Section 2, steel grade YST22, the molecular muscle.
You see, safety doesn't just magically happen at the construction site. It actually starts way down at the molecular level. The steel tubes used for scaffolding, they can't just be any random metal piping you find. They absolutely must be grade YST22. This fulfills precise chemical and mechanical properties defined in the IS 1161 standard. Plus, they need to be 40mm nominal bore heavy class tubes. And it doesn't stop there. All the general manufacturing of these steel scaffoldings and their fittings has to strictly satisfy the requirements laid out in IS 2750. These overlapping standards are absolutely crucial because they ensure every single tube can handle immense compressive and tensile loads without buckling on us.
Moving on to Section 3, Scaffold Support Component Anatomy, the nuts, bolts, and tubes.
So we've got our YSNT 22 grade steel, but how do we actually turn a giant pile of heavy class tubes into a rigid, walkable grid? Well, it comes down to understanding a really vital structural difference between two horizontal components that are super easy to confuse. First up, we have the transoms. These are the main, thick structural tubes that span completely across the horizontal ledgers. They tie the entire scaffold together transversely, basically sideways, providing that core stability and acting as the primary support for your working platform. Then you have the board bearers. These are your more versatile auxiliary tubes. They span directly between those transoms, or sometimes from a ledger to a wall, and their one specific job is to precisely support the wooden scaffold boards exactly where they're needed. So think of transoms as providing the macro skeleton, while board bearers support the specific footing.
But what happens when that skeleton runs into a massive gap in the building, like, say, a huge window opening? You obviously can't just stick a support tube into thin air. Enter the bridle. A bridle is a horizontal tube expertly slung between two existing put logs on either side of the gap. It basically creates a structural bridge, which allows you to support intermediate put logs right across the middle of that window opening. This maintains the platform's integrity in spots where wall support is just completely impossible.
Now, while a bridle gives you vertical support over a gap, a reveal tie gives you lateral stability. This is a tube that is actively jacked or wedged inside a window frame. Once it's rock solid inside that reveal, you take another tube, called a tie tube, and connect the main scaffold directly to it. This gives you a rigid lateral anchorage point, ensuring the scaffold never sways away from the building.
And of course, all that weight has to go somewhere, right? The base plate is a rigid steel plate sitting at the very bottom of the vertical upright. Its job is to take the massive, concentrated point load of the steel column and distribute it slightly. But right beneath that steel plate sits the sole plate. This is a much wider, ground-hugging timber member of adequate size. The timber sole plate takes the load from the steel base plate and safely distributes it over a much wider area of soft ground. Without it, the entire heavy-class steel structure would just sink right into the earth. Let's zoom out a bit for Section 4, Independent versus put-log scaffolds, standalone versus wall-supported. The crucial point here is how the structure actually manages its own weight. An independent scaffold, exactly like the name implies, has two full rows of vertical uprights. It stands essentially independent of the building structure. I mean, yes, it still needs to be tied for stability, but it carries its own vertical load entirely. A put-log scaffold, on the other hand, is seamlessly plugged right into the brick wall. It only has a single row of uprights on the outside. For the inside support, it relies entirely on the building's own load-bearing walls. So how exactly does it plug into the wall?
Well, it uses a pretty fascinating piece of hardware called a put-log end. It's a specially formed flattened tube end, which can sometimes be a detachable fitting designed specifically to slide directly into the brickwork or masonry joints of a wall. It literally allows the building itself to carry half the weight of the temporary working platform.
All right, on to Section 5, Maintenance and Storage Tutorial. Preserving the steel.
So we've built our scaffold, but how do we keep it safe over years of intense use? Because let's face it, the elements are a scaffold's worst enemy. Step 1 for longevity is surface protection. Atmospheric corrosion is relentless, so tubes absolutely must be protected by varnishing, painting, metallization, or hot-dipped galvanizing. Step 2 is safe cleaning. You have to use scraping or brushing to clean the tubes, but it must be done carefully so you don't damage that vital galvanizing layer underneath. And Step 3 is proper storage. You should never, ever store these steel tubes in contact with damp cement or lime, because prolonged contact leads to severe chemical degradation.
There are a few more really strict maintenance rules to follow too. You should always examine the moving parts of your fittings and storage and just discard any defective material that can't be perfectly repaired right away. Also, you have to cut out any deformed or bent tube sections. The standard specifically warns against repeated bending and straightening because it causes something called work hardening. Bending cold metal actually makes it incredibly brittle and prone to sudden, catastrophic snapping. If heat treatment is needed to fix a bend, that should only ever be applied by the original manufacturers. Oh, and finally, if you're working in a marine environment, always slap on a few extra coats of paint for good measure.
It really is an incredible system of rules and metallurgy, isn't it? Which leaves us with a provocative thought. As our architecture pushes the boundaries, building higher and faster than ever before, how will the very codes that ensure our safety, like IS 4114-1, need to evolve to meet the extreme demands of tomorrow's skyline? Thank you so much for joining me on this explainer. And remember, if you have liked this video, like, share, and subscribe to the ISO Automation Lab channel. We'll see you on the next deep dive.